Welcome back to session 2, a little more technical, also very DNV heavy, but that's not a bad thing. First off, anyway, is Thomas from Kongsberg, who will tell us about interoperability and running FMUs with special constraints. So without further ado, Thomas, stage is yours.
Thank you. You can hear me. So interoperability and FMUs with special constraints. What an exciting topic. I hope you're all ready to see how we can run those FMUs. So let's just get on with it. I'll start with a short introduction, just to make sure we're all on the same baseline when it comes to FMUs. Then I will continue with what are these constraints that we are talking about? Because constraints can mean lots of things. We're not talking about numerical constraints in this sense, talking more about software constraints. I'll finish by giving you a overview of some reference architectures that I think can help us with running FMUs with special constraints. So, on to the introduction, and let's start by introducing me. So, my name is Thomas, as I said. I work for Kongsberg Maritime, have a master's degree in marine technology with specialization in cybernetics. Worked for Rolls-Royce and then for Kongsberg. I didn't change jobs. My company was bought by KM, so now I work there. In OSP, I was involved with the use case virtual commissioning. Check it out on the web, it's fun. I've also been involved with making the reference modes you can find online and configuring some of the reference cases. I just want to limit the scope of the presentation a bit. We will be talking about FMI 2.x. There is a 1.x version and a 3.x. Those are slightly different, but the most popular one as of now is 2.x. We will also limit the discussion to FMI for co-simulation. And co-simulation means that everything you need to solve your equations are inside the FMU. So you don't need an additional solver. Everything is there, nice and dandy. We'll also limit ourselves to FMUs that are loaded dynamically. That is, they are shared as shared libraries. There are FMUs that are shared as source that you can compile into your applications, but we'll not talk about those. So, FMU demystified. What is this black box? It's nothing fancy really. It's just a collection of shared libraries implementing something called the FMI interface, which is just a standardized way of running an application. You take those files, put them in a platform-specific folder, together with a description of its inputs and outputs. You can put some additional stuff in there as well, such as the source, documentation, and resources. Then you take that bunch of files and you compress it into a zip file. And then you say, I don't want to name it something.zip, so I'll name it something.fmu instead. And there you have an FMU. Just a fancy zip archive with some DLLs or shared objects. That's really it. Roughly, the call sequence for an FMU looks like this. Of course, after you loaded the DLL, you have to do some unzipping and dynamic loading and stuff. But the call sequence after that is quite simple. You start by instantiating the FMU, just giving it system resources. Then it sets up the experiment. Then you just run step, advancing forward in time until you are satisfied. And then you clean up after yourself, which is a good thing to do when running software. Of course, there are other nuances to this. You can, of course, read inputs, you can set inputs and read outputs, tune parameters and stuff. And there's also some additional functions, but those are not of importance here. How do you make FMUs? We've seen some examples already today. You can make them by hand using wrappers for different programming languages. The standard itself is C, meaning you can implement them manually if you want. Just implement the prototypes and you're good to go. Or you can use an SDK such as FMI CPP to make your life easier. So you don't have to re-implement all those common functions every time, which is kind of boring. The great thing is that you can also make them from tools. And we'll see examples of that as well. You can take your Symlink spaghetti diagram and just make it into an FMU. And then you can share that FMU with someone else, and they can run it without having Symlink or have to look at your diagram at all. There are 78 tools currently. Those are taken from the FMI homepage that supports Code Simulation 2.0 export. And of those, 39 to Linux and 75 to Windows. I wish there were more for Linux, to be honest. So now you know all about FMUs, because the FMU is the basic building block we are simulating using the OSP platform. So what is stopping you from running those damn FMUs? Well, lots of things really. Here are some of the constraint flavors. You have operating systems that are causing issues. Maybe you don't have enough hardware. Maybe your network is struggling and you don't have access to the things you need. Maybe you have special runtime dependencies that you need to load. Or maybe someone has locked your FMU behind a horrible license. When it comes to OSS, we have the classics, Windows and Unix family, because the FMUs are compiled to specific systems. So you can't necessarily run a Unix FMU on a Windows machine, and vice versa. You have FMUs that runs nicely on the desktop because they need access to window manager things and other desktop applications. And you have FMUs that run nicely on server machines because they don't need a desktop environment at all. Bitness comes into play. You can compile FMUs for 32-bit and 64-bit systems. You can usually run 32-bit on 64 systems, but it's not that easy to do the opposite. Typical examples of OS constraints is running a simulation where you have both Windows and Linux FMUs. How do you do that if you only have Windows or only have Linux? Maybe you have to run them together or inside a real-time control system that uses a very specific platform that causes issues. Onto hardware constraints. So, hardware. Maybe your FMU needs the graphics card to do some heavy work. Maybe it offloads things onto all the cores. It's running some graphics, drawing stuff. Maybe it's running a very parallel algorithm that uses all the thousands of cores in your GPU. Maybe it communicates to someone externally through the network or through a serial interface. Then you need a network or serial card. I mean, most computers have a network card. Maybe if you have a very thin Mac, it doesn't. CPU architecture, bitness comes into play as well, because that's also a property of the CPU. In addition, there are CPUs with different instruction sets, which basically means what language does your CPU talk. If your FMU is not compiled to that language, you can't run it on that system. Or we'll see you can, but not that easily. So the two most common architectures are ARM and Intel x64. You heard of those. Maybe your FMU has a large memory footprint. It uses up all your available memory. It thinks it's Chrome just chugging all that memory. Maybe it's doing heavy matrix calculations, or maybe it's just caching everything it does in memory. Maybe it's logging to your disk. It shouldn't, but you have naughty FMUs that do that. All logging should happen through the code simulation algorithm. Maybe it does some caching, or maybe the FMU itself is huge, so it takes up all your hard drive space. Typical hardware constraints I've seen, running stuff like collision avoidance algorithms, where most things are offloaded onto the GPU because you're kind of doing chess where you have one move that results in 10 moves that results in 100 moves, etc. You can have FMUs doing visualization, then you need the GPU unless you want to run at 2 frames per second, which is not very nice. And I also work with the network FMUs where you need to talk to an external interface. So these are not hardware constraints, but those are mainly network service constraints. So what do you need on the network to run your FMU? Maybe it's offloading something to a server, it needs to contact the server. Maybe it's controlling something externally. Maybe you have an FMU controlling the lights in this room through an API. Then it needs to be able to contact that API. Maybe it's communicating to other systems, like a network FMU. Or other FMUs, such as through proxy FMU, which is a way of distributing your FMUs across multiple machines. Or maybe it uses a proprietary protocol. Maybe it's fetching weather data from Yr. Maybe it's fetching traffic data from marine traffic, who knows? Maybe it needs to contact a licensed server. Examples of network constraints. I've been running FMUs that uses MQTT, a communication protocol where it needs to contact a broker, which is a centralized guy just shuffling information around. Among the reference modes, you can find FMUs generating and sending and receiving NMEA messages. You need to be able to send them somewhere. And license services are already mentioned. And that's actually a very, no, that was too early. We will come to licenses. Runtime dependencies. That are things that the FMU needs when it starts. External code that it loads into the system. That can be everything from the language standard libraries, if it's compiled with C++, for instance, or other types of languages. Can be system dependent things. Can be a very fancy external library you found that solves all your problems and you just need to have it in your FMU. Or it can be a perfectly good in-house library that some genius at your workplace made that everyone now uses. And that also got to be in there or in your system so the FMU can get it. Runtimes, it's just a fancy way of saying external dependencies. It's often a collection of stuff from a tool or something that you need to have installed or available so that FMU can use it at runtime. Some examples I've encountered. The first one is especially annoying when you try to run FMUs in containers, where you want to have small containers. Then you want to compile with other libraries than GNU libc, which is the standard library for C made by GNU. But you want to use Muscle instead, which is the smaller and nicer library. AimSim is a simulation tool that exports FMUs, but it comes with lots of dependencies. Addition, maybe you have a FMU that uses Python, then you need Python installed. Maybe you have one using Java, then you need Java installed. And Boost is a very well-known CPP library that I've used myself in FMUs and I've seen others use as well. Licenses. My favorite topic. I really hate them. They are making your life so difficult. They usually make it more difficult for the end user to run stuff. But the sad truth is that we have to deal with it. They come in different flavors. You have things like file-based licenses, where you just get the file from your vendor, need to serve that to your FMU somehow. Put it inside the FMU, maybe in the resource folder, or give it the path using a parameter. You have hardware locked licenses. Maybe the FMU is locked to a specific machine based on its MAC address or some other hardware property. Then you can't run it distributed. You have to run it on that specific machine, else it won't work. You can have key-based, that's maybe a bit contrived. Thinking of like this old PC games where you had to type in an activation key to prove that you own the game. legally, well, can make those kind of software locks. So they're also applicable to FMUs. Peripheral based. We have systems in our simulator where you have to put in a physical USB in a machine, and then the software will look for that USB and say, okay, I'm allowed to run because I can find that device. I mean, it's slightly more distributed than node locked because you can move the USB from different machines. Kind of annoying though. Floating and network licensing, that's a classic one, where you run a license server with a certain number of licenses that it can give out. The issue is that you often run out of licenses because people forget to give them back, and then you can't do what you want. The last one is also maybe a bit contrived. You can have metered FMUs. I can see that it will become a thing where you actually pay per use or pay per hour for using an FMU, especially if it comes from someone else, maybe through some service. I really wish I had the license, the permit on the right-hand side there. Some examples, vSIM have node locked and network licenses. So you have to tell me if I'm wrong, but I think it has. We had an engine model in OSP that had a time limited license. So now we can't use it anymore. Both MATLAB and AIMSIM have node locked and network licenses, which makes them a bit more complicated to run. I think MATLAB has solved it by now, that you can actually export self-contained FMUs. AIMSIM has not. So now we've seen all the constraints, all the things that might stop you from doing your simulations. So how do we overcome these constraints so that we can actually do what we want to do? So let's take a look at some reference architectures. But what do you need to implement these architectures? Well, you need a way to run FMUs, of course. If you can't run the FMU, it's useless. You need to be able to run it locally, that is on your local machine, such as this laptop. And you need a way to run it distributedly. So maybe you run some things on that laptop, and you run some things on that laptop, and some things on that phone, but they need to be able to communicate with each other in some way. And of course, you need enough machines to cover all your hardware requirements and OS requirements. And you need all the license runtime services that your FMUs are dependent on. So luckily, OSP gives us some of these tools. We have libcosym, which is the general library for running FMUs locally. You have proxy FMU, which gives you the ability to run them on other machines together with libcosym, which is really, really neat. You have configuration options through the OSP system structure file that tells you how your simulation is supposed to look. You have a model description extension and the interface specification that allows you to simplify interfaces, making it easier to connect your FMUs. We will see some hands-on approaches, or you will get a hands-on approach to some of these things in the workshop later today. We will also probably most likely need virtualization of some kind. For those of you that don't know what that is, it's just running a computer in a computer, basically. I won't go into detail. I'll just name drop some technologies that you can use. KVM, part of the Linux kernel, hence why it's named kernel-based virtual machines. Fine if you're running Linux. Docker, a more lightweight approach where you run containers. They're not full virtual machines, but they're really good for running some kind of applications. VMware, very famous vendor of virtual machine software. And Hyper-V is the Windows implementation of virtualization. So on to the architectures themselves. I will start with a very simple one, and then we will go for increasing complexity. So let's just get on with it. This is the simplest way of running an FMU, and you You've probably done it, every one of you. You just install libcosym on your machine. You run the FMU. That's it. Really, really simple. And that's actually the pro. It's super duper easy to install and execute and monitor and get out everything you want. But it has lots of issues. You have to pollute your machine with all the dependencies you need, which is really annoying when you start to have multiple versions of the same dependencies. And then you go to DLL hell and you don't want to be there. It's limited by your hardware. If you run 1,000 million FMUs, then your machine might melt because it can't power them all. It's not very scalable and not very redundant. If your machine dies, the simulation dies with it. Not very good. And of course, you can't run Windows and Linux FMUs in the same simulation. So it's fine if you have all the dependencies locally, but it's not very good in the long run. We can do better. We can install a virtualization technology on your machine. That enables you to run another OS on top of your existing one. So you can run FMUs that are support local execution directly on your machine. You can run the rest in the VM. So it's very good. It requires proxy FMU because it's kind of distributed, even though it's really not, because you still only have one machine. So it's slightly better since you can now run both Windows and Linux FMUs at the same time. Hooray. And it's still fairly simple to set up. I mean, simple is depends on who asks, I guess, but I think it's not that difficult. You get partial isolation between the VM and your local machine, and you don't have to pollute your local machine with lots of dependencies. Still you have got to have some dependencies for native execution, but it's better. You're still limited by hardware, and it's still not very scalable nor redundant because you're still running everything on one machine. We can do even better. We can just buy more hardware. We can buy more computers, and we can set them up so they can talk to each other and run FMUs. They can be different machines running different OSs. Some of them might be dedicated, have dedicated hardware, such as GPUs. And some of them might run virtual software as well. So this is a very simple distributed network. Just have 3 machines connected to some kind of net, and they can talk. One is running Windows, running libcosym. It's the master algorithm, deciding when to step. It runs some FMUs that supports Windows. That's it. Have another machine running Linux, runs proxy FMU, so it can talk to the master algorithm. It runs a license server as well, so FMUs, regardless of where they are, can contact the license server and say, and the license server can say, okay, you are permitted to run. And the FMU can say, thank you, license server. And you can also run a control system distro alongside it if you can't virtualize your control system. And it can talk to the FMU or simulation through the network. This is similar to what we're doing at the simulation cluster here, which works very fine, except we don't run that many FMUs though. Pros here is that you distribute your load across multiple machines, so your single machine won't melt from overload. You can also run FMUs for all kinds of OSs in the same simulation. It's more flexible because you can run more stuff, really, and it's easier to get more stuff in there. And it's more scalable since it's easier to plug in a new machine. And if one of your machine dies, some of the others can take over. And if you have a good system, you won't necessarily lose your work. Of course, it's more expensive because you need more hardware. You need computers and switches and maybe routers, and you need cables and power is very expensive these days. Actually, it's gotten cheaper, I think. and the architecture is more complex. So it's more difficult to manage and implement and configure. And of course, if you have some dedicated critical machines and they go down, your whole system will just crash and burn. And you have no necessarily not network isolation. I mean, depends on how you set up your network. You can have it or you cannot have it. But you at least have hardware isolation if you want. So the last example is taking it even a step further. So now I'm thinking, let's just get rid of the dedicated machines and try to make the machines that are our backbone as similar as possible. Let's make them all run Linux, for instance, and we virtualize everything. Because then it's easier to manage. Of course, you can still have some special hardware because you probably won't get away from that. It will always be some system that requires something different. But all our requirements are hopefully covered by virtualization, because then it doesn't matter which machine runs what, they can all run everything. It may look like something like this, where we have a common OS backbone with a common virtualization stack. Can be Docker, KVM, can have multiple virtualization technologies if you want to. You probably will, because some things require virtual machines, other things requires containers. And then you run all the usual stuff, FMUs, libcalsim, license services, and control systems. But now they can run anywhere. And it's very scalable and flexible, because things can just be shuffled around. So if something dies, you just move it. And you can run Windows, Linux, and all kinds of OS dependent FMUs, and multiple simulation instances if you want to. Your hardware layer is uniform, so it's much more easier to have a centralized and common configuration management system. You can have hardware and network isolation if you want. Of course, now things are starting to get a bit complex, because you have to manage all of these resources and storage and machines and everything. So you might need someone with very special competence for managing and setting up these things. So maybe you should think about using some cloud provider or some service that handles this. But that's up to you. I mean, depends on where you want to put your money and where you want to specialize. That concludes my presentation. So now you know how to run any kind of FMU. Questions?
Thank you, Thomas. Yeah, I have a very important question. When you find the person handing out these runs once and permits, please see if you can get one for me too, because I imagine that being both very useful and controversial at home with the missus, at least. All right. We'll have, Stian will come to you with the microphone. What questions or comments do we have for Thomas?
Yes, we have a question over there.
Thank you. Thanks a lot for this very clear presentation. Maybe a simple question. How much complexity did you reach so far in terms of, for example, numbers of FMUs, traffic, maybe load between different virtual machine or different FMUs? What is the scale that has been reached so far?
Okay, so you're asking about scale and what kind of limitations we've seen there?
Yeah.
That is very, very dependent on what kind of simulation you're running. And of course, the hardware that is your backbone. I can only talk from experience running the simulation cluster we have here. That runs mostly containers. It's been running some FMUs. There we have 12 fairly old machines that are running probably around, it's at the scale of 20 to 30 containers at the same time, running different control systems, and together with HMI and all the network communication. we haven't had any issues there so far. It's more difficult when you start coupling it with visualization, because then you need very powerful machines. We have a dome downstairs where you do visualization, and there we have, I think it's 6 machines with or gaming machines that's actually doing the visualization. Yeah, so I mean, it's really a implementation specific issue. I think it's going to, you won't run into problems when you have smaller systems like you build for yourself. But if you're running really large scale stuff, I'm talking like thousands and hundreds of thousands of FMUs and instances, then it's going to be an issue. And then you might want to switch to someone that actually manages this for you. Hope that answered your question. Yeah. Wait for the microphone. It's actually a bit difficult to hear you down here, so it's nice if you get the microphone.
Hello. Thank you, Thomas, for the clear presentation. And OSP and Simulation Trust Center are new to me. I don't have experience with them. And my question is how what you presented here related to the Simulation Trust Center of DNV?
Yeah, okay, that's an interesting question, and I think it's a very good misunderstanding to clean up. So OSP consists of some critical components. You have some software that is libcosim dimension. It's a software for executing FMUs. So it can step FMUs forward and it can manipulate FMUs. And then you have proxy FMU, which allows libcosim to control execution on remote machines. And then you have all the configuration formats that it also provides, so you can connect your FMUs. Simulation Trust Center is DNV using those tools to implement their own service that they want to provide to different to people making FMUs and to people that want to use FMUs. So that's the difference. So Citrus is just an implementation using libcosim, but libcosim and all its parts are free and open for everyone to use to make their own stuff. So what Kevin showed us earlier was another implementation using the OSP software parts.
Okay, and in a project, what would be the ideal stepwise approach if you want to have it running at the Simulation Trust Center?
In the Simulation Trust Center?
Yeah, is it better that you have everything arranged locally and then you take it there? Or is it a better approach to slowly build up your environment on the Simulation Trust Center?
Depends on where you are. And now DNV is probably going to be a bit angry with me. But if you've never run an FMU before, I think the best way is to start by actually exporting an FMU and running it locally on your machine or on multiple machines. Maybe try out proxy FMU when you are familiar with running things locally, and then try to expand. And if you see that you actually need to share your models with someone else and collaborate, then maybe you can start looking at the Simulation Trust Center. Or maybe if you need to do large-scale simulations, because that's one of the things that the Trust Center does. It actually distributes things across nodes, so it can scale and it can isolate your FMUs. Yeah.
Any more questions or comments for Thomas? No? Well, Thomas, thank you very much. I enjoyed that greatly. I learned something, which is mainly to stay away from all of this and just run my stuff locally.
Yeah, that's way more fun.
That's not much fun, I guess.